I haven't put the screen down yet because I wanted to share a couple of things that I'm afraid you can't see. But one of our speaker's Twitter. I know the journalism students like to follow new people on Twitter. It's at FL Climate Center, at FL Climate Center. And then on the other side, I've written down the link to the climate tools, the climate and weather tools that David Zierden will be talking about after his lecture, and it is http://bit.ly, bit.ly/climate_tools. And Dorothy is going to put this on the Facebook stream so that people can see the link. This is a live Facebook stream, and we will share the link with you if you'd like to have it. It's on the College of Journalism website, and then we'll share the permanent link after if you'd like to have that. So I'm Cynthia Barnett. I'd like to welcome everyone on behalf of the University of Florida's Bob Graham Center for Public Service, which has sponsored this event, and the College of Journalism and Communications, which is hosting us, and the Florida Climate Institute, thank you, and several other partners who have helped us get the word out about our wonderful guest speaker. I'm here to introduce Florida climatologist David Zierden. So this check-in on what we know about how climate change is impacting Florida was organized for the Graham Center's Civic Scholars Program, which is a great undergraduate research experience that this semester is sending 67 scholars into all 67 Florida counties to research local impacts of climate change. So we open this lecture to the larger community because climate change is such a pressing topic in all 16 of our colleges at UF, and indeed on the minds of many of our students, whether they are studying hard sciences or the liberal arts and sciences. So here in the College of Journalism and Communications, this topic used to be the purview of students interested in environmental journalism, but now all kinds of reporters, including the sports reporters, increasingly come ask me how to find information about extreme heat, or how much the 30 NFL cities have warmed during football season. The answer is an average 23 degrees Fahrenheit over the last half century. David Zierden is used to fielding climate questions from reporters, from farmers, from water and forestry managers, public health officials, and many others, having served since 2006 as our state climatologist at the Florida Climate Center, which is part of the Center for Ocean Atmospheric Prediction Studies at Florida State University. A native of Panama City, David earned his bachelor's and master's degrees in meteorology from FSU and is a member of the American Association of State Climatologists, the American Meteorological Society, and the Florida Climate Institute. So after his lecture, David will take some time to answer your questions, and then we have scheduled a brief workshop, maybe 20 or 30 minutes, to introduce students to the data tools that he uses every day in his work to try and understand climate trends. So those of you who are in the Civic Scholars group, I think you know this, but you are required to stay for the workshop. The rest of you are welcome to stay if you'd like to. And Civic Scholars 2, during the workshop is when you will check in with your mentor. So you definitely want to stay for the workshop to get your introduction to the data tools that you'll be using when you look up things about your counties, such as temperature and precipitation records. So for the rest of the students here, if you're not familiar with the Graham Center and its many opportunities, including Civic Scholars, please come by the second floor of Q Hall and get involved in an organization that offers opportunities in public service, civic engagement, and leadership to all students in all majors. I want to emphasize that the challenges of our world, including this one, need all of you. Thank you very much, and please join me in welcoming David Zierden.
Thank you very much for the kind introduction, Cynthia, and it's a pleasure to be here with the Grand Center students and the University of Florida College of Journalism. I think when Cynthia first invited me here, I pictured a cozy little classroom lecture with a few dozen people, and now I've got an auditorium full and live streaming and really important people in the audience. I'm a little nervous, but no, it's really a pleasure to be here. I'm going to go ahead and start this lecture, and I'm going to start it with this still photo. It's from a video capture that's available on YouTube. This was taken in the eye of Hurricane Michael from Mexico Beach, looking west towards Tyndall Air Force Base. And as she said, I grew up in Panama City. I still have family there. So this one kind of hit hard and was a little personal. Life in Panama City is 18 months later is still far from normal. Interestingly, unemployment is actually down because so many workers have left the county due to a lack of medium and low-income housing. Enrollment in the public schools is down 20 to 30% still. So impact's still being felt. But this is a still image from a video that's available on YouTube taken by some storm chasers. The full video is about 5 minutes. I'd encourage you to give it a look. It's the most spectacular footage from the eye of a Category 5 hurricane that I've ever seen. Here in this you can see where the pine forest is basically leveled, hardly a tree left standing. And you can also see the eye wall in the distance, and you can even see that stadium structure of the eye wall, which is a feature of fully developed hurricanes. As a full-fledged weather nerd all my life, experiencing the eye of a major hurricane was always kind of on my bucket list. After seeing the damage in this, I'm very fine with just seeing it on video. All right, so we'll go ahead and get into the subject of tonight's talk, and I want to kind of frame this climate change talk with talking about the different threats, the weather and climate threats that we as a society have to live with, especially here in Florida. And here in Florida, the main threats are drought, extreme rainfall and flooding, hurricanes and wind damage from severe weather events. Here we also have to worry about severe freezes and their impact on the citrus industry, winter vegetable industry, crops that are vulnerable to freezes. We also have to deal with heat stress. Not only these episodic heat waves, but also long periods of elevated temperatures can do their share of damage also. And of course, near and dear to us is sea level rise. So we're going to kind of focus on these threats throughout the talk. Let me say something that might be surprising. Climate change is not bringing any new threats from the weather and climate side. We've had all these threats, we've been living with them all along. Now don't get me wrong, climate change, there's growing evidence that it is changing the nature of some or all of these threats, either their frequency or their severity, but as to now, it's not bringing any new threats. And one simple illustration to kind of frame this, it's a very oversimplified definition of what risk is. And basically, you can think of risk as the threat or the likelihood of an extreme event occurring times the exposure or the impact or vulnerability we have to that threat. Well, this can be represented on a simple graph like this. Over on the y-axis is the threat or the probability of an event. The x-axis is the amount of impact it has on us. Well, even without climate change, we're not going to be able to reduce the risk or the threat of these extreme events. With climate change, it's a high likelihood that this threat is actually going to increase. How much depends on how much carbon dioxide and greenhouse gases the global community continues to pump into the atmosphere, but it's not going to go down. However, we can better our space on this graph by reducing our vulnerability. An extreme illustration of this is an iconic photo from Hurricane Michael on Mexico Beach. You see where whole city blocks have just been leveled by the storm surge, except for this one house that was built by an engineer who engineered this house to like double the building standards and made it very hardened and hurricane proof. And it worked out well. It only withstood minor damages. That's one example of reducing our vulnerability. However, I don't think that's a workable model for the middle and lower income families that have lived along the coast for generations. It's not going to work for us. Well, now let's start digging into the climate and some of the observed trends, both globally and locally. And the first one I think we've all seen before. This is the famous Keeling curve. It's a very accurate measurement of carbon dioxide concentrations in the atmosphere. The laboratory was set up on the top of Mauna Loa in the Pacific, in the Hawaiian Islands back in 1956, I believe. And these very accurate measurements that represent the global concentration have been made continuously since 1956. And what we see is a very steady rise, even an exponential rise, in the carbon dioxide concentrations around the world. And this is a direct result of human activity and the burning of fossil fuels. What this graph doesn't show that's even more alarming is by looking at ice cores from Antarctica. They can drill down almost a mile deep through almost yearly layers of ice and sample the tiny air bubbles caught inside and get CO2 concentrations back almost 1 million years, which encompasses several ice age cycles around the globe. Well, in that million-year record, which is before the advent of human civilization, carbon dioxide levels have never been this high. So this is a grand experiment that we're doing on the planet that we really don't know where it's going. At the same time, this is another graph we're probably all familiar with. This is a graph of global average temperature, yearly global average temperature. This is tracked by 4 or 5 centers around the world. Their results basically agree within just a small margin of uncertainty. But this is the one from NOAA, and it shows since 1900 a steady increase in global average temperature over the last century or more. A little bit of multi-decadal variability in the 1940s and 1960s, but that's overlaid on top of this steadily increasing trend. Another takeaway from this graph is you'll notice each of the last 5 years have been the warmest on record in this data set. And that includes 2019, the numbers just came in. It was the second warmest year ever on record. The only one warmer was 2016, where we were under the influence of a very strong El Nino in the Pacific Ocean that I'll talk more about a little later. What's interesting also is not all areas of the globe are warming at the same rate. We see the most warming in the higher latitudes of the continents of North America, Eurasia, North America, which is cut off here. There's a couple little bitty exceptions that you might not even be able to see them. There's this patch off the coast of Greenland that, due to changes in ocean circulation, has been consistently colder than normal. There's also one little blue dot over Georgia and Alabama. We're starting to catch up, but this was known as the global warming hole. It was one area of the globe that was not responding to this rise in global average temperature. But I think those days are gone, as I'll show you as we get further into the talk. So let's do that now. Let's take a closer look at U.S. and even Florida temperatures. Here's a map of historical rankings for the 2019 calendar year by state across the United States. And what we see is North Carolina and Georgia experienced their warmest year on record. Florida was second warmest, as was South Carolina. Alabama, third warmest on record since 1895. Here in Florida, we've really been heating up in the last 5 years. Out of the last 57 months of monthly temperature averaged across the state, 54 of them have been warmer than normal. Only 3 months in the last 5 years have been cooler than normal. This also includes the last 20 months in a row. And during that 5 years, 6 of the 12 months set all-time records. So we've been warming up quickly. Interestingly, overnight temperatures are being affected more than the daytime, afternoon high temperatures. And this graph at the bottom really shows you what's been going on in Florida. It's the statewide average temperature, smooth with a 5-year running average. And what we see is the last couple data points on this spiking way up, eclipsing the rest of the record by a large portion. We're now 2 degrees Fahrenheit warmer than this 1990 to 2010 baseline period. So it's looking pretty clear that we are in a new climate regime here in the state of Florida. Yeah, I talked about overnight temperatures being affected more than daytime highs, and this is an illustration of that. This is the same kind of graph. This is actually just, instead of annual temperatures, this is summertime temperatures, June through August, for Climate Division 2, which is basically most of North Florida. And what we see, record pretty steady until we get to about 1980, then a dramatic increase in overnight temperatures of over 2 degrees Fahrenheit. One reason this might be important, in 2018 and 2017, then again in 2019, peanut yields in North Florida were inexplicably down. We had plenty of rainfall. In 2017, some blame indirect impacts from Hurricane Irma, but other farmers said no, we were starting to see our fields deteriorate even before the hurricane. It's still kind of an unknown. They're still looking for why these peanut yields are depressed, but these overnight temperatures could be part of the problem, affecting the physiology of the plant. Other aspects of our temperature are not as affected as much. Let's look at winter temperature, and there's an interesting story to go with this too. This is now Climate Division 1, which is the western Florida panhandle, and these are winter temperatures, December through February, since 1895. We see a lot of year-to-year variability, kind of some warmer winters in the 1930s and 1950s, definitely colder winters in the 70s and 80s. Now we're coming back up again. Well, this was really important to this small electric cooperative in the Panhandle called Talquin Electric, kind of their business model. During the summertime, their demand or load demand is pretty stable because it's hot and everyone runs their air conditioning, and it's pretty stable, pretty predictable. It's the unpredictable winter temperatures that made or break their profits for the year. A cold winter, a lot of people would turn on their heat pumps, and then the auxiliary heat strips would kick in. Electric demand would go sky high. The meters would run. They'd make money. But this was getting increasingly hard to predict. We talked to them about the El Nino-La Nina cycle, and that helped them out a lot predicting their yearly profits. But also, we talked about climate change and that they might need to start factoring that into their long-time profit and demand projections. And as you can see, this is an example. This is for Lake City, Florida, just to our north. And this graph is simply the lowest temperature each winter since about 1894. And we see we have as low as 6 degrees here in 1899. What was it? 7 degrees in 1985, I believe that is. but really no trend in what our coldest temperatures of the winter are, at least in North Florida. Let's talk more about severe freezes. John Attaway is retired citrus expert here at University of Florida. He wrote this book on the history of Florida citrus freezes. It's got a lot of great information about the old agricultural weather service that was run out of Ruskin. But anyway, he identified about a dozen of these catastrophic freezes that had a major impact on the citrus industry. And prior to 1894, between 1835 and 1894, we had very few freezes. And in fact, this is a picture of a citrus grove near Palatka, Florida, here well north of where they grow citrus now. You see the size of these trees, they must be 30 to 40 years old and had not suffered any damage from freezes. So there was an extended period with no freezes in the 19th century. Then we had a cluster of freezes towards the end of the century and the turn of the century, devastated the citrus industry here in North Florida. It moved further down the state towards around Orlando, Lakeland, that area. Then we get to the 77 through 1989, another cluster of really devastating freezes that pushed the citrus industry even further south, where now it's centered around Immokalee and the western side of Lake Okeechobee. So the question is, are these going to be a thing of the past with climate change? I think that's a possibility. I'm not seeing it in the data as of yet, but it's something we should keep in mind. I think very smart people are starting to explore more and more citrus production north in the state or even in the South Georgia. One more thing on extreme cold, and I might even get myself into trouble. I hope Jeff Huckman helps me out if I dig myself too deep. We talked about the science of the polar vortex. It's been popular in the media in the last few years when we get one of these severe Arctic outbreaks. It's blamed on the polar vortex. And there's even been some speculation that it's tied to climate change and changes in our circulation. And the way the theory goes is the polar vortex, or even the polar jet stream, is driven by the difference in temperature and pressure, very cold, relatively low pressure over the Arctic, warmer and higher pressure in the mid-latitudes and the tropics, drives this jet stream system. Well, the Arctic is warming at twice the rate of the rest of the globe. So we're reducing that difference between the Arctic and the lower latitudes. So as we reduce that difference, this jet stream moves a little slower and is more apt to these big troughs and ridges, and it's these troughs that allow the intrusion of Arctic air. Still a very unproven theory. There's been some work published saying that it is a legitimate effect, and there's more evidence in the summer than in the winter time, but it's still a very open area of research. Okay, the trends in temperature are pretty clear. Now when we start looking at precipitation, now it gets a little muddier. And I'll show you here. First, let's look at recent precipitation. This is similar to that temperature map. This is the historical rank for rainfall for the year 2019, going back to 1895 for the lower 48. And it was a very rainy year. Over the whole contiguous U.S., it ranked as the second wettest. Last year was actually the fourth wettest. So we've been kind of in a rainy pattern looking at the whole United States. We see up here these dark green states all had their rainiest year on record, played havoc with the corn crop this year and other grain production up in the grain belt. Here in Florida, we were pretty middle of the road. But it's very difficult to see any trends in rainfall, especially if you start looking more locally at statewide rainfall totals. And this is just state average over the state of Florida, rainfall, yearly rainfall totals since 1895. You see there really is no trend. but we have this tremendous year-to-year variability, which is where the real risk lies right now. And as you can see, we can have as little as 22 inches of rainfall in 1 year. I'm sorry, this isn't yearly. This is warm season, which is really important for Florida, May through September. So this is the warm season, rainy season, rainfall that really drives our hydrologic systems across the peninsula. We can have as few as 22 inches, as much as double of that. And you see this tremendous year-to-year variability. Some of that is tied to this El Nino La Nina cycle that I'll go into in a little bit. However, there is one aspect of rainfall where we are seeing a trend, and that's a change in the heavy precipitation events. And these figures are from the U.S. National Climate Assessment. Over on the left, this bar graph shows the number of days across the southeast with rainfall of 3 inches or more, which most would consider a heavy event. You see a steady increase, mostly decade by decade, to where we're now over 1 day per year with 3 inches or more, where earlier we were less than 1 day per year. But these are relatively rare events. The statistics are not robust. If you look at it across the area, the blue dots are where we're actually seeing a decrease in heavy rainfall. The red dots an increase, which are more than the blue dots, so that's why we get this graph. So, the science says as the atmosphere warms, it can hold more moisture, which will lead to heavier rainfall events. And more and more evidence is showing that that is already occurring, but the statistics of it still kind of a tough nut to crack. And actually, Dan Duarte here with the Florida Climate Institute at University of Florida, he did a similar study where he looked at rainfall events at different thresholds, and he found a tremendous increase in the number of 6-inch events or more, which are closer to really catastrophic flooding events. Now we're going to kind of go the opposite way, look at trends in droughts. Even more nebulous, as drought is not only related to the amount of rainfall you get, but it's the entire water cycle, evapotranspiration, water demand, all of it. This is the old Palmer Drought Severity Index, averaged across the state of Florida since 1895. The orange dips, if you will, are when we're in periods of drought, where this index is negative. The green spikes when we're moister than normal. And again, you see the tremendous year-to-year variability, but it does appear like there's an increase in the frequency of drought over the past 20 years or so. Whether this can be blamed entirely on climate change, I'm not sure. Again, there's this El Nino La Nina cycle that plays a big role, as I'll show you in just a minute. But certainly, even if rainfall remains the same, increased temperature and increased evapotranspiration will drive that water balance and create longer, more severe periods of drought all on its own. On this subject. Humans have dealt with sea level rise before. This is a graph of a geological record of sea level rise as we came out of the last ice age 22,000 years ago. And as these enormous continental ice sheets over Eurasia and North America melted, the sea level rise over the course of tens of thousands of years, nearly over 100 meters. So, tremendous amount of sea level rise as we came out of the last glacial period. But also, notice on this map, about 8,000 or 10,000 years ago, we're still in the midst of that rise. As we got into the modern civilization period, we've really leveled out. But this 8,000 to 10,000 years ago is very important. This was some work from archaeologists at Florida State University studying, paleo records and looking for indigenous artifacts. They found evidence of settlements out on the continental shelf in 50 to 60 feet of water. So 8,000 years ago, this was where the shoreline was, where the settlements were, and these tribes actually followed the coastland inland as the sea level continued to rise. This doesn't have much to do with climate change, but it's very interesting nonetheless. So now let's talk about modern sea level rise. There are two causes for sea level rise, so only two. One is a general warming of the oceans. As ocean water warms, it expands, takes up more room, so the sea surface rises. That's called the steric contribution. And as of today, the majority of sea level rise, a little over 50%, is from the warming of the oceans, as shown by this graph. These two blue bars show the contribution just from the warming of the ocean of current sea level rise, and it's over 50%. The other mechanism is by the melting of continental ice sheets and glaciers. Keyword being continental ice sheets. The massive ice sheet that we all know is losing mass every year over the Arctic Ocean, it's already floating on the ocean and has already displaced the water there. So it's not really contributing much to sea level rise. It's the continental ice sheets that do it. And here we see in yellow is melt from Greenland, from other glaciers in the blue, from Antarctic in this gray. So those are the relative contributions as of today. Where it gets really tricky is we have a good handle on, as the Earth and ocean continues to warm, how much this ocean warming contribution is going to continue to rise. What the science doesn't know as well is how are these continental ice sheets going to react to a warming climate? How quickly will they melt? So there's a lot more uncertainty on where these contributions are going to be in the next 100 or more years. So how do we measure sea level rise? There's two primary ways. One is a network of tide gauges around the world, some of them with daily records going back over 100 years. Over here on the right-hand side is a map representation of these tide gauges, and the size of the arrow shows the relative rate of sea level rise at each of these tide stations. But one thing you'll notice about the distribution of these tide stations, very heavily weighted towards North America, where population is greater and more coastline. Not nearly as many observations in the southern hemisphere, where there's a lot more oceans. So there's a bias there. There's also a bias over time, a lot more of these tide stations over the last 50 or 60 years than there were prior to World War II. So it's not a perfect data set, but no data set is. Like this shows the relative rate of sea level rise around the United States coast. You'll notice some places it's greater, like the coast of Louisiana, where in addition to sea level rise, there's also tremendous subsidence from the channeling of the Mississippi River and the lack of sedimentation and what oils has done over the years. It's all causing the land to sink. So not all of that is from global warming. Some of it is from other human activities. And up here in Alaska, sea level is actually decreasing because it's still undergoing crustal rebound from losing the ice sheets during the last ice age. But here in Florida, we don't have a lot of geologic processes going on, so our tide gauges pretty closely match the global rate of sea level rise. Here's the tide gauge of Pensacola, Florida, since about 1920, and what we see is a fairly steady rate of sea level rise at about 2.3 millimeters per year, which equates to about 8 inches per century. So that's the current rate along the Florida Gulf Coast. We're not really seeing any acceleration of that rate as of yet. Here's our second tool to measure sea level rise. And these have been around since about 1992. It's a satellite called an altimeter. These altimeters very accurately measure the height of the sea surface from space, a tolerance of just a few millimeters, which is a technological marvel to me. But we have these altimeters, and now we have this altimeter record of sea level and sea level rise since 1992. And one of the cool things they show us is the rate of sea level rise is not uniform around the world. much greater over here in the western Pacific, where the water temperature is much warmer. Over in the eastern Pacific, where you have cold water upwelling, a much lower rate of sea level rise, especially like along the California coast of South America. So it's not uniform around the world. But anyway, if we put all this information together, we get this one graph that's straight out of the latest U.S. National Climate Assessment. And the black line here, especially starting around 1900, represents the tide gauge record. This little white line is now the satellite record since 1992. We see a total rise in sea level since 1900 of about 9 inches or so. And then at the end are the different possible sea level rise scenarios as we go out to year 2100. Some take-homes from this graph. The latest research shows that both looking at the tide gauge record and altimeters, that now we are starting to see an acceleration of that rate, which is scary, because an acceleration of that rate means these higher scenarios are more likely. And in fact, some even argue that this low scenario, which is basically a continuation of the current rate, is already off the table. It's a very low probability that we see sea level continue to rise at that low rate. Somewhere in the rate of 1.5 to even up to 8 feet of sea level rise is what's possible by 2100. I will caution, these higher scenarios are from running the climate models with a very high emissions in them, which currently we're not even quite matching, so these might be the worst of the worst case scenario, but certainly higher rates are certainly more possible than anything closer to this lower rate. So, a lot of uncertainty on what over the next 100 or 200 years, what the rate of sea level rise is going to be or what the acceleration might be. But even if it's on the low side, that doesn't mean it doesn't create tremendous problems. As we know full well in Miami Beach, where we see the sunny day flooding happening more and more frequently, other coastal cities like Charleston and Norfolk, Virginia, running into the same problems. And this tide gauge graph really illustrates it well. This is from Virginia Key, right on the University of Miami campus. Got a record since 1996, but what you'll see is, notice this 4-foot level. Prior to 2015, that 4-foot level was only eclipsed under the influence of a major hurricane, a close call or hit by a major hurricane. However, since 2015, just these astronomical king tides have eclipsed that 4-foot mark. So that's been happening every year over the past 3 or 4 years now. All right, and kind of our last threat that I'm going to get to today, let's talk about observed trends in hurricanes. And most of what I've been talking about, except for the sea level rise, has been what we've been able to observe in the historical data, or what we can observe through direct observations. In a little bit I'll talk about the model projections and what they might mean for the coming 100 years or more. But we're still on just observed trends. Hurricanes. Let's go back a few years to 2016. As we entered the hurricane season of 2016, we were in an unprecedented hurricane drought. It had been 10 years since a major hurricane, category 3, 4, or 5, had hit anywhere in the United States. And it had been that same 10-year period, no hurricane of any strength had hit the state of Florida. Both unprecedented streaks without a hurricane. But there's an old saying in baseball that a player will play to the back of his card. And what that means is you got the old baseball card with the picture of the player, but on the back has his lifetime statistics. So a player might have hot streaks and slumps, but over the course of a long season, he's going to be close to those we had Hurricane Hermine hit Tallahassee, which broke Florida's streak. 2017, we had Harvey, which broke the U.S. streak of major hurricanes, followed immediately by Irma and Maria. Then in 2018, we had Hurricane Michael. We had close calls from Dorian and Matthew, so we're definitely in a hot streak now. But if we look worldwide, let's talk about the frequency or number of hurricanes. And if we look worldwide, this top graph shows the annual number of hurricanes around the world, or tropical cyclones of hurricane strength. The bottom is tropical cyclones of tropical storm strength. No, I'm sorry, I got that backwards. Number of hurricane strength storms on the bottom, tropical storm strength on the top. But both lines you see are fairly stable across time since 1970. So we really haven't seen an increase in the occurrence of tropical cyclones across the world. But there are other things we can say. Jim Elsner with geography at Florida State University, he published that the very strongest storms each year, as represented by these circles, are actually getting, the strength of them is getting stronger, and that this is tied directly to warming sea surface temperature and climate change. More and more studies are showing that we're getting increasing rainfall from hurricanes and tropical systems. A couple interesting studies by scientists at NOAA and others that forward motion of hurricanes, especially in the Atlantic Basin, might be getting slower, which has big implications. The slower a storm moves, like Hurricane Dorian, the longer the coast is subjected to the dire impacts, and the more rain it's going to drop. So, big impact if indeed storms are moving slower. And another study shows that the tracks may be shifting further to the north. So, while the number's not changing, other aspects of tropical cyclones may be. So, I can't do a talk without going back to my roots and talking about climate variability. In spite of all these trends we're seeing or not seeing, we still have to deal with the year-to-year changes in our climate. And some of these are more or less random, but others can be tied directly, especially to the El Nino, La Nina cycle in the Pacific Ocean. And I'm not going to go too in-depth, but I'll just try to simply explain what this is and how it impacts our climate in a few slides. Basically, El Nino is when this area of the central Pacific Ocean along the equator, all the way from the coast of South America to the international date line, warms several degrees Celsius warmer than normal. A tremendous change in a big area of the Pacific Ocean. And these are satellite images that show the changes in sea surface temperatures for two of our last biggest El Ninos in 1997 and 2015. At the same time, or part of the cycle, the same area of the Pacific Ocean can cool several degrees cooler than normal. And once again, that has major impacts for our climate patterns. And this is kind of our conceptual model on how it works. When we have an El Nino in place, represented by this top graph, all this extra heat and moisture in the Pacific Ocean strengthens the subtropical jet stream, guides storms, winter storms, cold fronts, frequent raininess along the northern Gulf Coast, and especially the state of Florida is greatly impacted. We can see 40 to 60% more rainfall than normal in the summer dry season when we have one of these El Ninos in place. La Nina, the opposite, where you have cool water now in the Pacific Ocean. Now the polar jet stream's the dominant player. The storm tracks kind of go up the Mississippi Valley, but it leaves Florida and the southeast drier and warmer than normal during the winter months. Real quickly, you can see how that affects our climate. These are temperature composites. If you put all the El Nino and La Nina events together and see what the departure from normal is, when you have El Nino in place, we're usually several degrees colder than normal just due to the increased cloudiness and rainfall. During La Nina phases, several degrees warmer than normal during the winter months. Similarly, if we look at rainfall, 30% or more rainfall than normal across Florida and the northern Gulf Coast during the El Nino events. 30 to 50% less than normal during the La Nina events. Let me skip this one. Let me show you some of the direct impacts from this cycle. Remember the Palmer Drought Index that I showed earlier? This is that same drought index, only this is for Florida Climate Division 2, which is again this North Florida area. And again, when these orange dips, or when it's in periods of drought, drier than normal, the green spikes, wetter than normal. Down here is the index that we track El Nino and La Nina with. These red spikes are when it's warmer than normal in the Pacific, and we have the El Nino phase going on, like 1997, like 2015. The blue dips are when we have the cold water, or La Nina, in place. I told you, La Nina brings warmer temperatures, 30 to 50% less rainfall. Notice the direct correlation with the periods of drought. 2000 through 2002. Again, 2010 through 2012, when the oyster fishery crashed in Apalachicola because of drought being one of the players. But you see a very direct correlation between this drought index and the Pacific sea surface temperatures. And one other take home, the El Nino events tend to only last 1 year. These La Nina events that bring us drought can often last 2 or 3 years. Okay, so that's climate variability. Now we're going to switch gears and take a quick look at what some of the climate projections tell us. What are our tools for projecting the climate out 100 years or more? Or the only real tool are climate models. What are climate models? They're very close to weather prediction models that we see on the Weather Channel every day, or especially during hurricane season. They use the same basic equations. It looks like a fairly simple set of 6 equations. They're called the primitive equations, but there's a lot of details in each of these, and these are differential equations that need to be integrated out in time to make a forecast. And they need to be integrated on a grid, both horizontally and vertically, around the world. So, both climate and weather models use these same physics, same equations, but there are some key differences. The weather prediction only needs to go out 10 to 14 days, and it's very dependent on initial conditions. That's why we spend so much money on our observation system and network of weather balloons around the world and surface observations and satellite. The better we can get the initial conditions, the better the forecast. Climate models depend more on boundary forcing, whether it's the solar output or greenhouse gases. And we look more for changes in patterns rather than snapshots like we look for in weather predictions. The fact that we have to integrate these climate models out 100 years or more introduces a lot of sources of error, internal variability, numeric instability, a lot of problems when you're trying to tackle climate. In addition to, you've got to get the ocean right, we know more and more, in order to get the atmosphere right. And so we've got to get the ocean right out hundreds of years and have both the ocean and atmosphere talking to each other. An incredibly complicated problem. But they are the best tool we have. One other kind of aspect of climate models, I'm often asked, there's about 3 or more dozen around the world that are commonly accepted in the science. I'm often asked, which one is best? It depends. Some do some things better, others do other things better. But it's generally accepted that if you average all the models together, you get what is called the model ensemble average. That's more accurate than any one model. So that's what we see here with the U.S. National Assessment. It shows projected changes in temperature by the mid-21st century here. Lower emissions scenario on the left, the higher emission scenario on the right. and what they project by the end of the 21st century. Again, lower emissions, higher emissions. They all show warming, and there's general agreement among all the models that the Earth and North America are going to continue to warm as emissions continue to increase. Very good agreement among the models on temperature. Here in Florida, because we're surrounded by water, we get a little bit less temperature change than the interior of the United States. But we feel a little bit more confident about these kind of predictions, certainly in the direction of these predictions. Rainfall is a tougher nut to crack. These models, you've got to get the microphysics of clouds and cloud formation and precipitation processes. You got to get those right, but we don't have enough computer power to put in full physics, so we got to make approximations, we call them parameterizations. So, very difficult to get the rainfall right in these climate models. And the projections, same type of thing from the U.S. National Assessment, show this. Some places it's drier than normal, some places wetter than normal, some general agreement across the northern United States, but everywhere it's hashed, that's where there's a lot of disagreement among the models, even in the direction of either more or less. So a lot of uncertainty when talking about changes in rainfall. Changes in tropical cyclones. I kind of talked about this, but I kind of list some of the impacts that we know are happening or could be happening with tropical cyclones. Most confident, coastal flooding will 100% be worse from hurricanes and tropical storms. Even if intensity isn't increasing, we have sea level rise on top of storm surge. And if you're only talking 8 to 9 inches of sea level rise on top of a 15-foot storm surge, maybe there's not that much difference. But if you start talking 2 feet of sea level rise on top of a 3-foot storm surge, tremendous difference there, and a tremendous contribution. Hurricane or tropical cyclone rainfall is likely to increase, like I talked about earlier. Again, models agree with Dr. Elster's results that the intensity is likely to increase as oceans continue to warm. We're seeing some of that, like I say, with Dr. Elster's work, but other modeling studies are supporting this also. We still don't know what's going to happen with the number of tropical cyclones each year. Very simply, it takes just right conditions for a disturbance to turn into a tropical storm or a hurricane. It takes absolutely perfect conditions for it to grow to category 4 or 5 strength or maintain that strength. So while the sea temperature is warming and that provides fuels for hurricanes, the rest of the surrounding atmosphere, the amount of moisture in the atmosphere, unfavorable winds, we're not exactly sure how those are going to react as climate continues to change. So that's why we can't say a lot about the number of tropical cyclones. All right, let's just summarize some of our other threats. Sea level rise, we talked about a great deal. It's going to be at least the current rate, that's 100% guaranteed, likely higher. How much high? That's a big question. Temperature, a good model agreement that temperature is going to continue to increase as we continue to load the atmosphere with greenhouse gases. Drought, like I said, rising temperatures alone could increase the frequency and severity of drought, even if there aren't appreciable changes in rainfall. But if we put in changes to our seasonal cycle or something on top of that, it could get much worse. Still don't know about the severe freezes. There could be a change. Our last really severe winter was in this state was 2010. Last week, or was it the week before, it reached 40 degrees in Miami, which was the coldest they've measured there since 2010. So maybe these severe events are getting less likely, less frequent, less likely. I'm not sure I would bet my ranch on it yet. Rainfall, we can say we're getting more extreme events, but still very uncertain about changing seasonal patterns. Now, I'm about out of breath, and I've tried my best just to present the data and the facts up to this point. But now I'm going to take this time to go off the rails a little bit and editorialize. Let's talk about climate science communication. Who are the most notable figures you know that are spokesmen for climate science? Let me see. Most recently, Greta Thunberg, of course. Bill Nye, Al Gore, Leonardo DiCaprio. Anybody got another one? What? David Attenborough. What do they all have in common? None of them are climate scientists. At least astrophysics, they had Neil deGrasse Tyson and Stephen Hawking and Carl Sagan. They knew what they were talking about. Not that these others don't. I'm just saying that kind of a weakness that I see that climate science has not been as active in communicating it to the public. And there are some very good spokesmen out there that are getting more and more active. Michael Mann at Penn State University does a really good job. He's always in the news, always advocating. Marshall Shepard at University of Georgia. There's many others. So it's getting better, but I'd still say there's a problem there. But anyway, a couple years ago, this kind of was an internet meme. This was developed by Ed Maybach, who's the director for climate change communication at George Mason University. And he said you can summarize climate change, or at least get the conversation started, with 5 simple points. It's real. It's us. The experts agree. It's bad, but there's hope. I agree in spirit to these 5 simple points, but a little criticism. There's some emotional language in there, like bad and hope. I had an old coach that always said, hope is not a plan. And that certainly applies to this big, messy problem of climate change. So I didn't want to replace these, but I added my own 5 talking points. My first one is, science is not a belief system. It's gotten better in recent years, but I used to always get the question as a climate scientist, well, do you believe in climate change? Belief's got nothing to do with it. I'm a scientist. We look at facts, we experiment, we see what the data shows us. We build upon the body of knowledge one step at a time. But it's not a matter of whether I believe it or not. Also, it's a bad question to ask elected officials or those running for office. Do you believe in climate change? No, the right question should be, what is your plan to address climate change? Whether you believe it or not, that ship sailed long ago. Climate science is much broader than just global warming. There's many different aspects to climate change, which I showed today. There's also this underlying climate variability that we still have a lot to learn and glean from. The El Nino-La Nina cycle. I've been working for over 20 years with area farmers and others, trying to understand this better and how to use this information to make better decisions. So there's a lot of other aspects of climate science other than climate change. A funny little story that I'll just throw out. I just got a new deck. They put this brand new pine decking on. I didn't know, well, when do I need to put the weather seal on? And the guy says, oh no, it needs to dry for about 4 or 5 months. I'm like, oh. And then I thought, wait, April and early May is the driest season of the year around here. That'll be a perfect time to do it. So very simple. Use the climate information to plan your activities better. Okay. Another thing that kind of puts me back is when I hear someone say, the science is settled. Well, yeah, the science is settled when you talk about the Earth is warming is a direct result of the human emissions of greenhouse gas. Yes, that basic question is 100% settled. The devil is in the details that I showed you, and lots of areas where there is uncertainty. One I'll even throw out that's kind of being debated right now is there's a measure called climate equilibrium sensitivity. And what that is how much does a model or a technique show that the Earth is going to warm with a doubling of carbon dioxide? Kind of a very simple measure. But even the last global assessment from the IPCC, there's a tremendous range of uncertainty anywhere between 1.5 degrees Celsius to 4 degrees Celsius. So we still can't really nail down that simple measurement. And actually the latest round of climate model results that are going to be used for the next IPCC assessment shows even higher climate sensitivity. And scientists are trying to figure out why these differ from the earlier generation of models. That's still kind of an unknown question. So there's a lot that's not settled. I won't go into a lot of detail, but we always hear about the bad impacts of climate change and the losers. There are going to be some favorable opportunities that a changing climate brings, like citrus moving further north, just for example. So all the assessments agree that the negative impacts will far outweigh any positive impacts, but that doesn't mean we should ignore positive impacts. And my final point, it's not your fault. We got to this mess we're making of the climate together through industrialization, the Industrial Revolution, the technological revolution. Society has advanced and grown by leaps and bounds, all because of the availability of fossil fuels as a cheap and usable source of energy. We got here together. We don't have runaway climate change because you're driving a big pickup. I don't want to diffuse fault. I just don't think guilt should be used to motivate on climate action. There's plenty of other great reasons for climate action. And one more, close a little lighter maybe. This crowd might be a little young to remember Clint Eastwood in his heyday, and one of his most memorable movies, The Outlaw Josie Wales. Anyway, in a great scene in this movie, he's come to make peace or negotiate with this fierce Indian chief. And it's a great soliloquy. He says, "I come bringing words of death and words of life." And he gave him kind of two choices. So I got words of death and words of life for you to close with. Words of death. We've heard about this 1.5 degrees Celsius or 2 degrees Celsius targets that were greatly debated in the Paris Accord, a special report from the IPCC on them. 1.5 degrees is just not going to happen. That ship has sailed. We are already at 1 degree Celsius of warming. We're not slowing down our global emissions at all yet. Still a tremendous amount of CO2 and other greenhouse gases in the atmosphere. This one's impossible, in my opinion, and the opinion of a lot of experts. Even 2 degrees is going to be exceedingly difficult. And to get to some of these goals, let me tell you what we're looking at. To get to zero emissions globally, or even a 50% reduction, it's going to take a revolutionary transformation of our global energy, transportation, industrial, agricultural, economic, and even governing systems to get there. Really, really tough problem. So the point I'm kind of trying to make is, are these arbitrary goals, especially when you don't even know the carbon sensitivity in the models that well, might not be the most productive approach. So we'll switch to words of life. The political will, even in the United States, is changing rapidly. Climate's being discussed more and more as a political topic and in campaigns, and voters are responding more and more as an issue that's really important to them. So I've seen a tremendous change in just the last couple of years. The sooner and more extensive we do cut emissions, the more likely we're going to stave off the most dire consequences of climate change. So the more we can do, the sooner we can do it, hopefully the less harsh the impacts of climate change are and the more adaptable we are to them. And I'll leave you to this. personal choices absolutely matter. I'm not sure we're going to save the world by going vegan, but every little bit helps, and your personal choices and lifestyle absolutely matter. But they're not enough alone. We also need broad global policy changes to go along with them. They're both important, they both work hand in hand, and one way a personal choice can tie directly into policy choices is to vote. The more you vote and the more voters make climate a key issue, the more policy will be.
Thank you.
Oh, last slide. One more from the movie. We will endeavor to persevere. If you haven't seen the movie, you don't know what that means.
So we have built in some time for your questions. We'll take questions for a few minutes, and then the Graham Civic Scholars and the other students who would like to stay for the workshop, everyone is welcome to stay for the workshop. So who has a question? Dr. Mulkey in the back.
Most of the seniors showed that land use change was probably a major factor in the frequency of freezes. Would you care to elaborate on that? Is that true?
It is true, and it was certainly true during his study period. But what Dr. Mulkey is asking about is there, in addition to changes in carbon emissions, land use change can have a big impact on our temperature, whether it's heating of urbanized areas like Miami-Dade County, or Roger Pilkey Sr. showed in a study that draining of wetlands across central Florida actually promoted more nighttime cooling, especially in these severe freeze events, and actually increased the frequency of freeze events. And that absolutely held true during the study period, and there's still some of that impact going on. Whether the overriding air masses are warmer now, I'm not sure.
Thank you.
Yes.
3 degrees is mentioned in the mid-century and late century as the signal number for Florida. What signal number is Florida at today?
Today, over the last 5 years, we've been running about 2 degrees Fahrenheit, which is closer to 1.5, 1 1/3 degrees Celsius than the previous 20 or 30 years.
What is the number that we're starting off from? What is that single number that we're referencing?
Like for statewide average temperature?
No, it says 3 degrees warmer in Florida relative to
Oh.
what is that number?
That's compared to the 20th century average.
But what's the number?
Oh, it depends on where in Florida you are. North Florida, South Florida.
Huh.
Yeah.
So there's no number.
There was a question in the very
Yeah.
back. Yes.
So you put up a slide earlier that had the devastating freezes from like the 1800s to like the 80s or 90s.
Yes.
And they all were in December, January, and February. Is there, I mean, maybe anecdotally, but I feel like we get freezes later we've been seeing freezes in March now, which are more devastating to citrus specifically because it freezes the buds off of them. Like a freeze in March is much more dangerous to citrus than a freeze in January.
I'd have to look closely to see if there's a trend in that. He was asking about not necessarily freezes during the heart of winter, but the late season freezes that can be even more damaging. And I'd have to look more closely. I don't know if there's a trend in that or not. I can tell you that in Georgia and South Carolina, in recent years they've had more episodes where January and February are very warm, and so the peach and blueberry crops even start flowering earlier than they should, and then they get hit with the late season freeze, and that's been happening frequently to our north. But I'd have to look more closely here in Florida.
Yes, Jeff Huffman.
I wanted to commend you for an incredibly clear and concise presentation on the climate.
Well, thank you.
I wanted to also ask for clarification for all of us, actually. Of the period of normal, it's a 30-year running period, correct, in terms of day-to-day temperatures? Is that 1980 to 2010? So are we about to enter a new 30-year period of normal in 2011?
Yeah, Jeff was asking about what we consider normal, and yeah, it's actually a WMO, World Meteorological Organization standard that normal should be computed on 30-year periods, and here in the United States we recompute those normals every 10 years. So yeah, right now we're comparing our temperatures day to day to the 1980 through 2010 period, but those will be recomputed soon, or yeah, I guess after we finish 2020. It usually takes them about 6 months to do all the
Did I
computations.
say 2011? I'm like a decade behind. Sorry. All right. So normals will change.
Yes,
in a
they
year.
will.
Okay.
Who else? Does someone else? Yes, all the way in the back.
Talking about science communication, sometimes I get people telling me, the climate's changing, and you say it's our fault, but some scientists say that this is like a cyclical thing. What can I tell them to let them understand? Hey, look, this is actually a human generated issue.
That's a great question. Is how much is this? Or let me rephrase it. How much is actual human contribution? How much of it is natural? How much of it is cycle? How much is other factors? There are cycles, and we don't fully understand what we call internal variability of our climate system. But as you saw in that graph of global average temperatures, it's dwarfed by this monotonic increase from greenhouse gases. So it's much less than that. How much human activity? The consensus now is 100%. That you'll hear people talk about changes in the solar irradiance or changes in aerosols and volcanoes and stuff. Well, guess what? Smart climate scientists have factored all those into the models and their analysis, and the solar constant and the aerosols would actually tend to cool us a little bit. So all the warming we see, according to a broad consensus, is from greenhouse gases and human activity.
The next question is all the way in the back. Yes.
Hi, thank you for giving your presentation. At the end, you said that there needs to be economic reforms in order to solve climate change. In a world where 70% of emissions come from not only corporations, but the same 100 corporations, how radical and fundamental do you think those economic transformations have to be in order to solve the existential threat that is global warming?
I don't think I can answer that question. I delved into it in my last slide, but I'm not a policy person. I know it's just a tremendously difficult problem, and it will take tremendous transformation in order to solve it. But exactly how that will look in corporations or in democratic countries versus other forms of government, that's kind of out of my realm.
Okay, thank you.
I would invite you as well. Dorothy, is it tomorrow at 6 p.m., the history of the future of fossil fuels? There's a really terrific panel tomorrow night at Pew Hall, also a program of the Bob Graham Center, where we will have a panel of historians talking about the history of fossil fuels, but they're actually going to be talking about the future and this transition to which you refer. So I think it'll be a really fascinating discussion, and I would encourage you to come if you're interested in some of those questions. This is at 6 o'clock at Pew Hall. There was a question over here. Yes, go ahead.
So you work with a lot of data. So I was wondering what way, or what you like to see from like media, governments, I guess people as a whole, like as a way to most effectively communicate that data to initiate change in people's daily lives and policy and stuff like that. Because there's a lot of things, some of the things you mentioned in your PowerPoint, are things still being said across the media and government talking about stuff like that. How would you say is the best way to, I guess, change that what's being said?
That's a great question. With all this complicated data and science, how do you communicate it to get people to change and take action? And I'm sure I didn't do nearly as good a job of it tonight as I should. Two ways: telling stories and making it personal. It's got to be a personal connection to what's happening in the climate and what it means to you in order to really hit people and affect their actions. And just showing them reams and reams of data, which I did tonight, that's not always the most effective way.
Did I get everyone's questions? One more here.
I read an article recently about how the ozone layer is closing up, or it's like the smallest it's been in years. And I'm wondering, what effect do greenhouse gases have on the ozone layer, if any, or how they interact?
No, the greenhouse gases, carbon dioxide and methane, don't really impact the ozone layer. What caused that ozone hole over Antarctica a couple decades ago were CFCs, chlorofluorocarbons, in aerosols and freon and such. And it's actually a great example of international cooperation. Once scientists figured out the problem, what was the cause, these agents were outlawed. The ozone hole is getting smaller and smaller every year now. So direct action can have an impact. So it's a great story. I'm glad you brought it up.
So, okay, one more, last one.
You talked about winners and losers. Are there any states you might consider a winner in, like, maybe like North Carolina, for example, Western North Carolina,
That's a
with the
really
Smoky
good
Mountains?
question.
You have kind of a temperate rainforest there and more of a controlled macroclimate with the mountains there. Are there any states that you compare to that where, you know, there's not as much of an impact?
I'm not sure I can answer that on a wide range, but I will answer it with an article I read yesterday is that some forward-thinking investors are buying up lots of land higher up into Northern California and Oregon, anticipating that in 25 to 50 years, it's going to be prime wine growing region. So they're anticipating the changes there and already kind of trying to take advantage of that opportunity.
Okay, this really is the last question, and it's all the way in the back.
Hi, thank
Go,
you.
you are the last question.
You mentioned that you feel that climate scientists should take a more active role in communicating their data and what is happening. And we've been talking a lot in my classes about the balance between scientists maintaining credibility, as unbiased, producers of knowledge, and also advocating for what they know to be true, especially in the climate change debate. And I wondered if you could, if you have a take on that as a climate scientist.
Yeah, I do. She was asking about this problem of climate scientists being more engaged in education and outreach and even advocacy. And some are. Like I say, Michael Mann at Penn State University is very vocal, very good at communicating the climate science. I'm not sure I would go as far into the advocacy as he does, because I do want to keep a little bit of impartiality as a scientist, but it works for him and he does it very well. But there's also another big barrier to doing more of that, and that comes in the academic setting, is those on a tenure track, professors, you get credit for publications and for grants. You do not get professional credit much for outreach and education. That's not really going into your performance or your tenure portfolio. So that's a big obstacle there too, when a lot of the climate scientists are in academia.
I will throw out one last example on the credibility issue, and that is to take a look at Einstein, who was a terrific opponent of nuclear armament and worked very hard on that issue, and as you know, it did not impact his credibility in the long run, right? So I want to thank everyone for being here. I'm going to bring the formal part of the presentation to a close. The Graham Center Civic Scholars